Hello, this is your host Salomon Guajardo of DEITV. Welcome to episode 1, where I will discuss the Simpson Index of Diversity, which serves as an introduction to diversity measurement. There are two types of indices, probability-based indices and logarithmic-based indices. In this episode, I'm going to talk about the Simpson Index, which is a probability-based index. The other probability-based indices include the Hurlburt Index, the McIntosh Index, the Smith and Wilson Indices, and the Wilcox Index. In terms of the logarithmic-based indices, those include the Hill Index, the Hurlburt Index, the Shannon Index, the Sheldon Index, and the Smith-Wilson Indices. The Simpson Index of Diversity was created by Edward Hugh Simpson in 1949. It is based on the probability of similarity or difference. Theoretically, it has a range from 0 to 1. It is, when applied to demographic data, the data is reported as frequencies or percentages. Now there are biased and unbiased scores and standardized and unstandardized scores. Although the Simpson Index has a theoretical value of 0 to 1, the actual empirical value is based on the number of categories or groups. The formula for calculating the maximum value of the Simpson Index is k minus 1 over k, or 1 minus 1 over k. Again, the maximum possible diversity coefficient is based on the number of categories, and as the number of categories increases, the value of the Simpson Index increases to 1. When k equals 2, the maximum value is 0.5. When k equals 5, the maximum value is 0.8. If the number of groups goes up to 10, then the maximum value of the index is 0.9. The biased Simpson Index of Similarity or Concentration is generally represented in 3 ways. One is the sum of n squared over the total number of individuals squared. It can also be represented as n divided by big N squared, when that represents the number of each group divided by the total number of the population squared. And it also can be represented as the percentage of each group squared. And this gives the coefficient of concentration or similarity. In this example, the Simpson Concentration Index is 0.611, which basically is interpreted as the probability of 2 individuals selected randomly belonging to the same group is 61%, and it also shows a moderate level of concentration. Now, to obtain the Simpson Index of Diversity, it's essentially as 1 minus the concentration index. In this case, it's going to be 1 minus 0.611, and that equals 0.389. And that is the probability of 2 individuals selected randomly belonging to a different ethnic group, and that's 39%. And it also shows a moderate level of ethnic diversity. To obtain the Simpson Index of Evenness for ethnic diversity, or the standardized score, you take the diversity score, divide that by the maximum possible score. So in this case, it's going to be 0.389. Divide that by the 0.80 that we calculated in an earlier slide. When you divide 0.389 divided by 0.80, that gives you 0.49, which represents that the organization obtained 49% of the maximum possible value for ethnic diversity. To obtain an unbiased coefficient of similarity or concentration for ethnicity, you take the number of individuals of each group times the number of individuals minus 1. You do that for each group, and then you sum that product. So in this case, it's going to be, for Asians, it's going to be 2 times 2 minus 1, which is 2. For blacks, it's going to be 10 times 10 minus 1, that's going to be 90. And all the way till you get to some other race, which is going to be 3 times 3 minus 1, which is 2, which is 6. When you add that product up, it's going to be 6,066. And then you divide that product by the total number of individuals times the total number minus 1, which is going to be 9,900. In doing so, you get the coefficient of 607, which indicates that there's a 61% chance that if you select two individuals randomly, that they will belong to the same ethnic group. To obtain an unbiased diversity score for ethnicity, you take 1 minus 0.607, which is the coefficient of similarity of concentration. So 1 minus 0.607 equals 0.393, which indicates that there's a 39% chance that if you select two individuals randomly, that they will belong to a different ethnic group. To obtain an unbiased evenness or standardized score for ethnicity, you take the unbiased diversity score and you divide that by the maximum possible value. So when we do that, it's going to be 0.39, divide that by 0.80, that's going to yield 4.9, which indicates that the organization attained 49% of the maximum possible value for ethnic diversity. This slide provides a quick comparison of the biased and unbiased ethnic diversity scores calculated based on the formulas that are presented in the earlier slides. So here the biased concentration score is 0.611, the biased diversity score is 0.389, and remember we obtained the 3.89 by subtracting 6.11 from 1. The standardized bias score is 0.487, and remember this is calculated by dividing 3.89 by 0.80, so that yields the 4.87. When we apply the formulas for the unbiased scores, we have an unbiased concentration score of 0.607. When we subtract 0.607 from 1, we obtain the unbiased diversity score, which is 0.393. When we divide the 393 by the maximum possible score, we get a standardized unbiased score of 0.492. Now in general, what happens is that the diversity scores for the unbiased formulas increase for the diversity score and the standardized scores in comparison to the formulas for the bias scores. As we will see in a few seconds, when the numbers become extremely large, there's essentially no difference between the biased and unbiased scores. Here, I want to mention a couple of disadvantages of using the unbiased Simpson indices. One is that it applies to demographic and social diversity data. In some of the research, the Simpson index is used to assess, for example, revenue concentration. So using the formulas for the unbiased Simpson indices for revenue, although you can do it, it's not recommended. The other disadvantage of using the unbiased Simpson scores is that it clusters the diversity scores at the upper end of the measurement scale, and that's because organizations that are small, the unbiased score formulas tend to overstate the level of diversity for small populations or small groups. The other drawback to the unbiased Simpson scores is that it produces scores that exceed the maximum possible value, and I'll demonstrate that to you during the application of the indices. The application of the formulas. Another drawback to using the unbiased Simpson formulas is that it reduces the measurement variability, and that is because the scores are clustered at the upper end. The application of the unbiased formulas also reduces measurement efficiency, and that's because it requires more mathematical calculations to obtain a diversity score. And because it requires more mathematical calculations, it becomes less efficient. The other drawback to using the unbiased Simpson formulas is that it has the potential to underestimate the value of diversity in mid-sized or large organizations. The last drawback to the unbiased Simpson indices is that it requires that the data be reported as frequencies. So in addition to having formulas for calculating the biased and unbiased Simpson scores. There's also a formula for obtaining the diversity scores when the populations are finite, meaning that the number of individuals in an organization or population is restricted or capped at a particular level. So to calculate the concentration index for a finite population, it's going to be n, which is the small n, which represents the frequency of the group, times the frequency of the group minus 1. You divide that by the total number of individuals times the total number of individuals minus 1. So you sum that up, and that gives you the coefficient of concentration. To obtain the diversity score for the finite population, it's going to be 1 minus the concentration index. That gives you the diversity score. And then finally, to obtain a standardized score for a finite population, it's going to be the diversity score divided by the empirical maximum value, and again that's calculated by the number of groups minus 1 divided by the number of groups. Although I presented some examples of how to calculate the biased and unbiased Simpson scores, I'm going to apply the indices or the formulas to data in an Excel spreadsheet, and I'll go through the calculations in the cells, how to calculate the diversity scores, the unbiased and biased diversity scores, and also the standardized scores. And I'm going to apply that to gender, ethnicity, and then to a table. It's a contingency table that has gender and ethnicity data combined. And again, I'll go through this, how to calculate the similarity scores, how to calculate the diversity scores, and then how to calculate the evenness or standardized scores. As I mentioned several minutes ago, I'm going to apply the formulas for the unbiased and biased Simpson diversity scores to data. So what I'm going to do is I'm going to share my spreadsheet with you. So this spreadsheet was created prior to the lecture or to the presentation. And so what I'm going to do here is I'm going to apply the biased and unbiased formulas, and I'm going to apply it to this data. So here, as you can see, I have gender, 4 categories, so K equals 4. I have 65 males, 25 females, 5 of some other gender, and then 5 that are unclassified, for a total work group or workforce of 100 people. What I also did was I calculated the percentage for each category. So to get the percentage of males, it's going to be B4, which is 65 divided by the total, F4. And I did that for each category. So for females, it was 25 divided by 100. That gives me 0.25 and 25%. Now to calculate the biased Simpson concentration score or similarity score, I can do it 2 ways. The first way, I can use the frequency, which is going to be, for males, is going to be 65 times 65. I can use the power function in Excel, which equals the parentheses power B4, comma 2, and parentheses. So the comma 2, the 2, it means to use the exponent of 2 with the power of 2, or square the number. So I did that for each category. And recall that the formula is for obtaining the biased Simpson concentration score when using frequencies. It's going to be the sum of small n squared. So that's going to be each cell squared. Once you square each cell and add that up, you're going to divide that by big N, which is going to be the total number of people, 100, times 100. So here is going to be power of 4n, comma 2. And so there's the formula. So when you divide the product of the cells squared divided by the total number of individuals squared, that's going to give me 0.490. An alternative way of doing it is to use the percentages. And so what I did here, it's going to be 0.65 times 0.65. And you can see on the Excel spreadsheet, the formula is going to be parentheses, B5 times B5, and parentheses for the males. For the females, it's going to be plus parentheses C5 times C5 and parentheses, which is 0.25 times 0.25. I did the same thing for some other gender and for unclassified. I'm going to sum that up, and that gives me 0.490, which is the same as I did when I used the frequencies. Now to calculate the maximum score, remember it's going to be the number of categories or groups minus 1 divided by the total number of categories. So here is going to be 4 minus 1, which is 3 divided by 4, which is 0.75. Again, I already calculated the concentration score, which is 0.49, and here's the reference, which is reference G4. What I can do is that you can just drag that down, and that gives me the concentration score, again, for percentages by gender group. To calculate the diversity score, it's going to be 1 minus 0.49. That gives me 0.510. To calculate the bias standardized score or evenness score, that's going to be 0.51 divided by 0.75. And here in the cells, reference is going to be K4 minus I4. And again, that's going to be 0.68. So let me interpret what these numbers mean. So the concentration score of 0.49 means that there's a 49% chance that if I randomly select 2 individuals, that they would belong to the same gender group. If I interpret the diversity score, again, that's going to be 0.49 minus 1, 0.51. The 0.51 means that there's a 51% chance that if I select two individuals randomly, that they will be of different ethnic groups, different gender groups. When I calculate the bias standardized score, which is 0.51 divided by 0.75, that equals 0.68. That means that the department obtained 68% of the maximum value of 0.75. Now let me move on to the unbiased score. Again, the formula becomes more complex. And as I mentioned in the PowerPoint presentation, that the use of the unbiased formulas makes the index less efficient because it requires more mathematical operations. And here you can tell that the formula becomes a little bit more complex. So in order to obtain the unbiased concentration score, I have to get I have to go to each cell. So if I want to get the unbiased score for the males, it's going to be 65 times 64, which is 65 minus 1. Then I have to do that for the females, which is going to be 25 times 24. And the formula is C4 times C4 minus 1. I did the same thing for some other gender. And I did the same thing for unclassified. I add each of those products, and then I have to divide that by 100 times 99. And then the formula is going to be F4 times F4 minus 1. That gives me a concentration score of 0.485. And again, that concentration score means that if I randomly select 2 individuals, there's a 48% chance that they will be of the same gender group. When I come and calculate the unbiased diversity score, that's going to be 1 minus, it's going to be, 4.85 minus 1. Here's the formula. So it's going to be 1 minus N4. That gives me an unbiased diversity score of 0.515 or 0.52, which means that there is a 52% chance that if I select 2 individuals randomly, that they will belong to the same gender group. Now for the unbiased Simpson score for gender, is going to be the 0.515 divided by the maximum score of 0.75. That's going to be 0.687. So the department obtained 68% of the maximum possible value of 0.75. Well, I did the same thing for ethnicity. And so rather than going through the whole narrative on calculating the unbiased ethnic score, let me just focus on the percentages because it's a lot easier. Again, it's just the percentage times the percentage for each group. So for the Asians, it's going to be 0.05 times 0.05 plus 0.2 times 0.2 for the Black workforce, plus 0.5 times 0.5 for the Hispanic workforce, plus 0.5 times 0.5 for the white work group, and it's going to be 0.1 times 0.1 for some other race. Again, when I add those up, that gives me the concentration score of 0.325. And again, that means that if I randomly select two individuals, there's a 33% chance that they belong to the same ethnic group. Again, to calculate the maximum score, it's going to be 5 minus 1 divided by 5. So it's going to be 4 divided by 5 equals 0.80. Now to calculate the bias score for gender, it's going to be 3.5. Subtract that from 1. That's going to be 0.675, which means that there's a 68% chance that if I randomly select individuals, that they will belong to the same gender group. When I want to get the bias standardized score, that's going to be 0.675 divided by 0.80. That's 0.844, which means that the department obtained 84% of the maximum possible score of 0.80. Now to calculate the unbiased score for race, for ethnicity, I have to go through each cell. So it's going to be for the Asian group is going to be 5 times 4, which is B4 times B4 minus 1. Then I have to do the same thing for the Black work group, which is going to be 20 times 19, or C4 times C4 minus 1. I do the same thing for the Hispanic group, same thing for the white group, same thing for some other race group. I'm going to add each of those products, then I'm going to divide that by 100 times 99. And that's going to give me the unbiased concentration or similarity score of 0.318. So again, if I'm going to interpret this, it's going to be 32% chance that if I randomly select two individuals that will belong to the same ethnic group, to obtain the unbiased diversity score, I'm going to subtract 0.318 from 1, and that's going to give me 0.682. And that means there's a 68% chance that if I randomly select two individuals that belong to a different ethnic group, again, the 0.68 means 68% chance that if I randomly select two individuals, they belong to a different ethnic group. The unbiased standardized score is 0.85, and again, that's going to be 0.682. Divide that by 0.80, that's 0.85, which indicates that that the department obtained 85% of the maximum value of 0.80. Here I have gender listed by role, by ethnic group. So I have 3 males that are Asian, 2 females that are Asian, none that are some other gender, none that are unclassified, for a total Asian work group of 5. Here I have the distribution of gender by the Black workforce. I have the gender distribution by ethnic work group, the same for the white work group, and the same for the some other race group, which consists of 10 individuals distributed by male, female, some other gender, unclassified. Now, because I use the frequencies, the formula becomes extremely long. And again, I use the power function in Excel, so it's going to be the power times the cell, comma 2, and parentheses, so that's going to be 3 times 3, 2 times 2, 0 times 0, 0 times 0 for the Asian group by gender. For the blacks is going to be, for the black work group is going to be 13 times 13 plus 4 times 4 plus 2 times 2 plus 1 plus 1. So that's going to be, when I do that for each of the cells, the product of each cell is going to be added up, and then it's going to be divided by the total number of individuals, is 100 times 100. When I do that, that's going to give me a concentration coefficient, a biased concentration coefficient of 0.168. And then if I want the biased concentration score by gender by ethnicity, it's going to be 1.68 minus 1, which is 0.83. To obtain the biased standardized score, that's going to be 0.83 divided by 0.95. And again, the 95 is 20 minus 1 divided by 20, so it's 19 divided by 20. That gives me the maximum possible score of 0.95. So again, to calculate the biased standardized score is going to be 0.83 divided by 0.95. In this case, is AF4 divided by AD4. And so the department obtained 87% with a maximum possible value of 0.95. Again, if I want to do the unbiased scores, I have to go back to each cell, to the frequency. So for Asian, it's going to be 3 times 3 minus 1, which is going to be B4 times B4 minus 1. So that's going to be 6. For the Asian females, it's going to be 2 times 1, because it's going to be 2 minus 1 times 2. So C4 times C4 minus 1. It's going to be 2. 0 for some other group for Asian, 0 for unclassified. So I have to do that for each cell by ethnic group, by gender. I'm going to add each of those cell products up. Then I'm going to divide by the total. It's going to be n times the total minus 1, so it's going to be 100 times 99. When I do that, that's going to give me a product or a score, concentration score, similarity score of 0.16. So again, the interpretation of this 0.16 is if I randomly select 2 individuals that belong to the same ethnic and gender group. So then if I subtract the 0.16 from 1, that's going to give me the 0.84. So that means that there's an 84% chance that if I randomly select 2 individuals, they will be of the same gender and ethnic group. To obtain the unbiased standardized score, is going to be the 0.84 divided by the 0.95. So I have 0.84 divided by 0.95. And then the cell is for the spreadsheet is going to be AU4 divided by AD4. Again, that's if the groups are listed in a row. So here, what I did, here is a contingency table of the number of by gender and by race. So males is listed in the column, in the row rather. So it's going to be 3 males, Asians. For the black population, for the black work group, it's going to be 13 black males, 10 Hispanic males, 34 white males, and some other race is going to be 5 males, for a total of 65. Again, the maximum score is going to be 5 minus 1 divided by 5, so it's going to be 4 divided by 5 is 0.80. Because I'm using frequencies instead of percentages, I'm going to, again, get the power. I'm going to use the power function, which is going to square each cell. So here, for example, I have B5, comma 2, that's for the Asians, 3 times 3. For the black work group, it's going to be C5, comma 2, using the power function, so that's going to be 13 times 13. For the Hispanic males, it's going to be the power, comma, power, parentheses, D5, comma 2, and parentheses, so it's going to be 10 times 10. I do that for the white males, either for the some other race males. I'm going to use I'm going to add the cell products. I'm going to then divide that by the power of G5, comma square, comma 2, and parentheses, so it's going to be 65 times 65. That's going to give me a concentration score of 0.345, 35%. So there's a 35% chance that if I randomly select males, they would be of the same ethnic group. Now, if I just want to, if I can just drag down the formula, that's going to give me the number of, it's going to give me the concentration score for females by ethnic group. Let me go back to the male group. So again, to obtain the diversity score, that's going to be 1. It's going to be 0.3345 minus 1. That's going to give me the 0.655, which means that there's a 66% chance that if I randomly select a male, they will be of a different ethnic group. The biased standardized score is going to be 0.65 divided by 0.80. And that's going to give me, when I do that, here's the formula. K5 divided by I5, that's 0.818. So there's so the department obtained 82% of the maximum possible score for males by ethnicity. And I just drag that formula down. That gives me for each row for the females, some other group, or some other gender, unclassified. And the reason why I have the circles is to compare that to the unbiased scores. Again, if I do that for the unbiased scores, again, it's going to be B5 minus times B5 minus 1, and that's going to be for the males. For the Asian males, is going to be B5 times B5 minus 1, so it's 3 times 3 minus 1, which is 2, so it's 3 times 2. I do that for the black males, do that for the Hispanic males, all the way down to some other race. I'm going to add each of those cell products. Once I get the sum of the cell products, I'm going to divide that by 65 times 64. So then that gives me the unbiased concentration score of 0.335, which indicates that there's a 34% chance that if I select 2 males, they will be of the same ethnic group. Again, to calculate the diversity score, is going to be 0.335, subtract that from 1, is going to give me the 0.665. And again, that's 67% that if I randomly select 2 males, it will be of a different ethnic group. To calculate the unbiased standardized score is going to be 0.665, divide that by 0.80. That's going to give me 0.83. So that's 83. The department obtained 83% with a maximum possible score of 0.80 when the unbiased formula is used. As I mentioned in the PowerPoint presentation, one of the drawbacks of using the unbiased scores is that it generates scores that are above 1. And this is the case, as I mentioned, because of the small population. In this case, it's going to be the small work group of 5. So it generates scores that exceed the maximum possible value of 0.80. Again, if you look at some other gender, the score is 0.1. If you look at some unclassified, there are 5 individuals as unclassified. So when you use the unstandardized formula, the formula for the unstandardized scores, again, the standardized score is going to be 1.125, which exceeds, again, the maximum value of 0.80. What I did here was looked at gender diversity by ethnic group. Again, because there are four gender groups, it's going to be 3 divided by 4, which is 0.75. To calculate the bias concentration score, I have to go through each column, each cell by column. So it's going to be 3 times 3, which is, if I use the power function, it's going to be power parentheses B5 for the Asian males, comma 2 in parentheses plus B6, the power of B6, comma 2 in parentheses. So that's going to be 2 times 2. And I do that for each cell in the column. And then when I add each cell, the product of each cell, I'm going to have to divide that by 5 times 5, or using the power function, parentheses power B9, comma 2 in parentheses. So that gives me a concentration score of 0.52, which means that if I randomly select 2 Asians, it will be of the same gender group. And then what I can do is I can just drag those formulas across the row, and that gives me the concentration score for each ethnic group by gender, for gender. So then if I subtract the 5.2 from 1, that gives me a gender diversity score of 0.48 for the Asian workforce. So that means that there's a 40% chance that if I randomly select 2 Asians, it would be of the same gender. So then if I do the biased evenness score, standardized score, which is going to be 0.48 divided by 0.75, that means that the department for Asians, the department obtained 64% of the maximum value of 0.75 for the Asian workforce by gender, or for gender. Again, I can highlight the cells and then drag it across, and that gives me for each ethnic group by gender, for gender. Again, this is 0.51, so if I go back to the gender, if I go back to gender, here's the 5.1 for the biased. And the 6.8 corresponds to the 6.8 for the unbiased. I did the same thing by department. Again, so there are 20 cells. So when I divide the 20 cells by, subtract the 20 cells by 1, and then divide that by 20, so it's going to be 19 divided by 20, that gives me the maximum possible score, 0.95. Again, I got to square each cell. I'm going to square each cell and then divide that by the total number squared. That's going to give me 0.16, which corresponds to the cells under the spreadsheet for ethnicity. And if I subtract the 0.16 from the 1, that's going to give me a gender and a diversity score by gender by ethnicity of 0.83. So the 0.83 means that if I randomly select 2 individuals, they will be of the same gender and same ethnic group. In order to calculate the biased standardized score for gender and race, that's going to be the 0.83 divided by 0.95. That's 0.875. So the department obtained 88% of the maximum possible value for gender by race of 0.950. And I use the formulas for calculate the unbiased scores. Again, the formula for the unbiased scores is going to be for the Asians is going to be, for the Asian work group, it's going to be 3 times 3 minus 1, plus the Sal for the female Asian is going to be 2 times 2 minus 1, and I do that for some other gender and unclassified for the Asian workforce. I'm going to add the Sal products, and then I'm going to divide that by 5 times 5 minus 1. So this is going to be 5 times 4. That gives me the unbiased concentration score, 0.40. And then when I subtract 0.40 from 1, that's going to give me the 0.6. So that's the diversity score, the unbiased diversity score for the Asian workforce. And then when I divide 0.6 by the maximum possible score of 0.75, that's going to give me 0.80. So when the unbiased formula score is used for the Asian work group, it obtained 80% by the maximum possible score of 0.75. And again, I did that, so I just dragged the formula across for each ethnic group and also for gender for the department. Again, these unbiased scores for the department correspond with the gender scores in the spreadsheet for gender. I also obtained unbiased scores by gender by ethnicity. And that 0.616 corresponds to the score over for here in this spreadsheet, AB. Again, to obtain the unbiased diversity score is going to be the 0.16, subtract that from 1 is going to be 8.84. Again, to obtain the unbiased diversity score for gender and ethnicity is going to be the 0.84. So, divide that by the 0.95. And when the unbiased formula for gender and ethnicity is used, it indicates that the department obtained 88% of the maximum possible value of 0.95. Now, as I mentioned, the Simpson diversity index can be applied to revenue, and it has been applied to revenue in research. So here, what I have is I have the what I call the actual data revenue for this nonprofit, and then I'll discuss the revenue scenario after I discuss the actual data. So the total revenue for this nonprofit is $403,000. Of that total, corporate donations total $80,000. Individual donations total $250,000. Fundraising revenue is $45,000. Investments is $10,000, and total grants is $18,000. Again, when I sum that up, that is $403,000. I can get the percentage for each revenue item, or revenue source. So for the $80,000 for corporate donations, that accounts for 20% of the total revenue. Individual donations account for 62% of the total revenue. Fundraising accounts for 11%. Investments accounts for 0.2% or 2%. Grants accounts for 4%. And when you total that out, that's 100%. What I'm going to do is I'm going to focus on the utilization of the percentages because it's a lot easier. And you notice that I calculated the P squares with the percentage squares by avoiding using the power function in Excel. So I just used B5 times B5, which is 20 times 20, 0.20 times 0.20. plus C5 plus C times C5 in parentheses, which is 0.62 times 0.62. When I did that for fundraising, it's going to be parentheses D5 times D5 in parentheses, or 11 times 11, plus the product for investments, which is 0.2 times 0.2, plus the square of the grants for the percentage is going to be 0.4 times 0.4. That gives me a sum of the p squares of 0.439. That is the same equivalent and identical to the, if I were to use the frequencies and square the frequencies using the power function, summing the subproducts of each cell, divide that by the total number of the total revenue, which is 403,000 times 403,000. The number gets awfully large. Again, that's 0.43. The interpretation of this concentration index means that if I randomly select revenue dollars, they will be of the same revenue source. If I subtract the concentration score of 0.439 from 1, that's going to give me the diversity score of 0.56. Again, that's 61% chance that the revenue dollars will be of the same revenue source. When I divide the 0.61 by the maximum possible score of 0.80, that's going to give me the biased standardized score of 0.70, which means that the nonprofit obtains 70% of the maximum possible score of 0.80, given that there are 5 revenue sources. I also calculated the unbiased Simpson scores for revenue. And as I mentioned in the PowerPoint, once the numbers get extremely large, it doesn't really matter if you use the biased or unbiased formulas because they're going to generate the same coefficients. Again, if I look at it's going to generate the same diversity scores. Again, I applied the formula for the unbiased concentration scores. And again, the formula starts getting extremely long. So to obtain the unbiased score for corporate revenue is going to be B4 times B4 minus 1, and those are in parentheses. So it's going to be 80,000 minus 80,000 minus 1. The same thing for individual donations or revenue is going to be 250,000 times 250,000 minus 1. And I'm going to do that for each revenue source. Then I'm going to sum the product of each of those cells, and I'm going to divide that by the total number of the total revenue, which is going to be 403,000 times 403,000 minus 1. So that gives me a coefficient of 0.439. Again, if I subtract the 4.39 from 1, that's going to give me 0.516. Again, that means that there's if I select revenue from 2 revenue items randomly, there's a 56% chance that they'll be from different revenue sources. Again, the unbiased standardized score is going to be the 0.561 divided by the 0.71, the 0.80. Again, that's going to be 0.561 divided by 8.0. That's going to be the unbiased standardized score 7.1. And again, that means that the department obtains 70% of the maximum possible score of 0.80. Again, as I mentioned, I do not recommend using the unbiased score for revenue, especially since the numbers get very large and you're going to get the same identical score. What I did here for the revenue scenario 1, I'm just illustrating how increasing the corporate donations from 80,000 to 100,000 increases the percentage to 21%. If I keep the individual donations stable at 250,000, the percentage actually decreases to 53% because the revenue items for the revenue associated with the other revenue items I increased. For example, the funding revenue I increased to 75,000 from 45,000. I increased investment income from 10,000 to 20,000. That increased the percentage to 4%. Let's suppose that I obtain $30,000 in grants, which is an increase from the 18,000 in the previous year. Under the scenario, that makes it 6%. So when I square each percent, so it's going to be 21% times 21% plus 53% times 53% plus 60% times 16% plus 4% times 4% plus 6% times 6%. If I add those up, that gives me a concentration score of 0.35. That means that there's a 35% chance that if I randomly select revenue, there would be the same revenue source. Just for illustrative purposes, I also did that by the power function. For the frequencies, again, that obtains the same concentration score or coefficient. Again, the maximum score is the same. It's going to be 4 divided by 5 is 0.80. In other words, it's going to be 5 minus 1 divided by 5 based on the formula. It's going to be 0.80. The concentration score we already have, so I just put that equals to H9. The new diversity score is going to be 3.5, subtract that from 1. That's going to be 0.64. So now under this new revenue, under revenue scenario 1, there's a 64% chance that the revenue are going to come from the same revenue source. If I use the standardized score, the unstandardized score is going to be, let me click on the cell. It's going to be L9 divided by J9, which is going to be 0.648 divided by 0.80. That's going to give me 0.81. So that means that under the new revenue scenario, I obtained 81% of the maximum value of 0.80. And again, just for consistency, I did that for the unbiased scores. I applied the unbiased formula for the unbiased scores to the revenue scenario. And again, because the numbers are so large, using the formulas for the unbiased coefficients provides the same identical scores as for the biased scores. And again, this is because the numbers get so large that the unbiased score, the formula for the unbiased scores has no impact on the diversity score. Again, because again, I do not recommend using the unbiased scores when the numbers get so large, only because you're just do multiple calculations to obtain the same identical scores. So that concludes the application of the formulas to the gender data, to the ethnic data, to the gender by ethnic data using the Simpson scores. I'm going to stop sharing. And then I'm going to return back to the PowerPoint to add additional references, and then to provide a small little introduction to episode 2. Several of the recent books that I published with Cambridge Scholars Publishing address the Simpson Index. One of those books is Assessing Organizational Diversity with the Smith and Wilson Indices. Another book is Assessing the Validity of Diversity Indices. A third book that includes the Simpson Index is Assessing Organizational Diversity with Content Regression. In episode 2, 2 Smith and Wilson indices will be presented. Both of them are based on the Simpson Index. And consistent with episode 1, the 2 Smith and Wilson indices will be applied to the gender, ethnic, and gender and ethnic diversity data that was presented in episode 1. And this is to be consistent with episode 1, episode 2, and the forthcoming episodes that will discuss the additional probability and logarithm indices. So stay tuned to episode 2. Thank you.